Okay, so last week we did the bivariate data analysis, which forms the basis, really the idea of covariance, correlation forms the basis of all of the tests that we'll be talking about in this module. But we know them and tend to think of them, and we teach them separately. If you do statistics, they're not taught separately, they're taught all as part of the same general linear model. What we're going to do is start off looking at the normal distribution. So where does it come from? Why is it so pervasive? Then we'll look at the Z-score, the standardized normal distribution. This should be familiar to you from first year. T-tests again from first year, but we'll think of them as being really what we want to do is a Z-score. We just want to talk about standardized distances in the same way that correlation is the standardized covariance. But we can't, we have to do a thing that Gossip sorted out for us. And then we'll move on to the realm of Fisher. So extending the t-test to the ANOVA, because really they're the same thing. There is actually no formal difference between a t-test and an ANOVA with two levels. The normal distribution really is very common, and it should be. You should be able to find a whole lot of things which are normally distributed. And there's just a fraction of those. Basically, if you can think of something you can measure, it's reasonable to assume as a starting point it's going to be normally distributed. If you're going into the counts of something, then that's not quite the case. But for the most things that we measure, they should be normally distributed. And to see why, we can think of getting a normal distribution. How do you derive it? We can start with just the binomial distributions, heads and tails. So you toss a coin, it could be a head or it could be a tail. And then you toss it again, it could be a head or a tail, and so on. Okay, so if we take that idea of just tossing a coin, having a binomial distribution, and toss it lots and lots of times, what you can see here is a distribution of the number of heads and then the normal distribution that fits to it. And as you get more and more coin tosses, so there we are up to 100 tosses, I need to be careful how I say that, what we need, you can see that the distribution gets more and more like the normal distribution. And in fact, the normal distribution is the case when you have an infinite number of binomial processes. You have the normal distribution. So you can show mathematically that this is the normal distribution. And so the binomial distribution is, if you like, an approximation to a normal distribution. Of course, it's really the other way around. The norm is an approximation to a binomial distribution. What this means is that if we have some variable and we have an infinite number, a very large number of processes, each of which can tweak that variable up a bit or down a bit, so any one process can increase or decrease the value of that variable, it will be normally distributed. So anything that's complex, like us, the way that we think, if we can think of it, envisage it as being made up of lots of tiny little processes, each of which changes the output variable, our dependent variable, a little bit, you would expect it to be normally distributed, because we've got an awful lot of processes, each of which can change the dependent variable a little bit. It can either increase or decrease. And of course, although we might do things in continuous space, if you like, continuous variables, if you think what a computer does, it represents numbers as zeros and ones, as binary events. And you really don't need many of them to end up with very, very accurate, what looks like continuous data. So your computers, your tablets never store a number as a real number, so 1.376 is not stored in that way. It's stored as a number of binary bits. You can do that to very large precision with a small number of them. So we would expect pretty much anything that we measure to be normally distributed. Having said that, of course, we'll see later on in the course that pretty much anything you measure is not normally distributed. but the idea behind it is there. There is the normal distribution, so that big N mu sigma squared, and then that upside down A is for all x which are members of the real number. The function that gives the function of x that gives you the normal distribution is etc. etc. You do not have to memorize things. I just like putting it up because I always think it looks impressive. I used to start this module with some horrendous excessive equations and then start off with, so what we're going to do is derive these and see how they relate to analysing data. It had nothing to do with it, it was just to scare everyone. You don't need to know any of these formula. Anything in the grey boxes is not necessary, it's just there, as you'll see later. I'll even label it as being to remind me of what's going on. What that means is that we have to think of it as a normal distribution applies to continuous data, the real data numbers, rather than it being discrete ones. And it is described by two parameters, the mean and the variance. If you remember from a couple of lectures ago, of course, we can think of the variance, we can take its square root, think of it as being the standard deviation. Those are, in the sense of a normal distribution, interchangeable. We can have, quite obviously I hope, an infinite number of normal distributions. So any change in the mean is a new normal distribution. Any change in the variance is a new normal distribution. And that means that we've got to try and get our heads around too many things. What we want to do is to standardize things so that we only have to think of one normal distribution. So we're going to transform the data such that the mean of it is 0 and the variance is 1. Because we can do that very easily, we subtract our mean from each observation, so the mu, subtract it from the x, and divide by the standard deviation. What that does is normalize the variance. It happens to put it to 1, so it looks as though the standard deviation is being normalized, but it's actually the variance that we're normalizing to make it 1. Now, instead of having an infinite number of normal distributions, we can do this to any data set, to any values, so that we only ever have to think of a single normal distribution, the standardized one. Okay, so it's just a mathematical trick. We use the z-score so that we don't have to think of every possible normal distribution. We're dealing with a single normal distribution. And the advantage of that is that we can now use that to calculate the probabilities. If you remember, I was talking in several lectures ago about we can take our statistic, so in this case a z-score, it's just a statistic, and ask what is the probability of getting that value or more extreme. Okay, so we can do this formally by taking this distribution and putting it into a cumulative form and making it reach 1. So it goes from 0 to 1. And now we can just read off, for any z-score, we can read off the area to the left, which corresponds to the area in red here. These match up. And then we do 1 minus it, because the total is set to be 1. So once we've got a z-score, we know the probability that can be calculated from it. The probability of getting that z-score or less is directly calculable, and then you do 1 minus that probability to get the probability of getting more extreme. Okay, so now we can take any normal distribution, so any process, any value. If we can transform it into the z-score, so we know the mean, we know the standard deviation, we can now get the probability of getting that statistic, that z-score, or more. So that key assumption that you often see in statistics when people are talking about the data being normally distributed, if you remember from the bivariate lecture last week, it's actually the residuals, deviations from what you predict need to be normally distributed and evenly distributed. You don't want those devil's triangles. But if those things are normally distributed, we can always calculate the probabilities by converting any value into its z-score and reading it off. The problem with z-scores is you need to know the population values. You need to know the population mean mu and the population standard deviation sigma. So these guys we rarely know. In some instances we do. So when we're dealing with IQ tests, those have been carefully set to have a mean of 100 and the standard deviation I think is of 15. And so in that case we know the population parameters, but in general when we take a measure we don't know the population parameters. What we can do of course is use estimates of them. So we can take our sample and get our sample mean, and we can get the standard deviation of the sample, and that's quite straightforward. But they're estimates, they're not the actual values. Because they're estimates, there's uncertainty, particularly about the standard deviation. And that uncertainty, what is the variability, what's the standard deviation, means that that distribution that we have is no longer a Z distribution. It's the T distribution, and that's what Gossett worked out, the guy from Guinness. What it comes down to is because we don't know exactly what the mean and the standard deviation are, it could be a little bit higher or a little bit lower, and that means that that spreads out the Z distribution. And the amount that it spreads it out depends only on the uncertainty. And that's determined by the degrees of freedom, the sample size. Okay, so the black dotted line is the Z-scores. If we know what the mean and standard deviation are, we can create the standardized score, the Z-score. If we don't, then we end up with a T distribution, and its shape, how far it deviates from the Z-score, depends on the degrees of freedom. So if you've only got 1 degree of freedom, it's actually quite a long way out. From the green line is quite a long way from the dotted line. As you get up towards 5, it's getting close. The rule of thumb that everyone uses is if you're about, degrees of freedom are about 30, sample size of about 30, then you're very close to having the Z-score. It used to be, when people had to look these things up in tables, that that's where the tables would stop, at which point everyone assumed the Z-score. But we now have computers, and you can do these things analytically very quickly, and the computer can tell us. So we no longer have to default to pretending that we've got a true estimate of the sample mean and standard deviation. We can always use the sample estimates. What this means is that if you think that to get a Z-score bigger than 1.96, so that's 2.5% of the area, and there's 2.5% at this end, you need to get a larger value of T than you would for the Z. It's spreading this distribution out, flattening it and spreading it out. So it's still worth remembering that magic number of 1.96. I always round it to 2. And then use that to give you an indicator of whether you're likely to see a significant effect. So a T value bigger than 2 could be significant. Doesn't mean it is. It will depend on the degrees of freedom. And if your degrees of freedom are only 4 or 5, it won't be. So again, going back to the idea of power, what we want to do is have enough power so that that rule of thumb, 1.96 or 2, is going to be about right. Sample sizes really do matter. This will be a test of whether you've actually read the first and second year notes. We can think of the t-test as having 3 variants, but they are all variants. So the first one is a sample mean the same as a hypothesized mean? So if you hypothesize that your mean is going to be 2.7, however you get that 2.7, you take your sample mean, x bar, and the difference between it, and express it as a z-score, if you will. It'll be a t-distribution, but you divide by the standard deviation of that difference. If we have two samples, we take the difference between the two means and standardize it by dividing by the standard deviation of the difference between the means, and so on. So all t-tests are dividing by the standard deviation of whatever it is on the top line. So if it's the difference between two means, it's the standard deviation, the difference between the means. The third option is often the paired or within subjects t-test. But what we're really doing is looking at the mean difference. We take, for each participant, we take the difference in their scores and ask, is that 0? Okay, so that's really doing a differenced score, so the difference between the two observations. Asking, is that value, the average of that, divided by the standard deviation of those differences. So it's doing a test against a hypothesized mean of 0 of the differences. Okay, so we've got 3 variants of it. We're going to have a very quick detour about standard errors of the mean. They're the standard deviation of an estimate. And it's a measure of the accuracy, or the size of the error, with which we think we might have made that estimate, so we call them standard errors. But calculation-wise, they're just a standard deviation. We're going to have a brief foray out, because once you realize that you can do 2 ways of calculating that standard deviation, ANOVA becomes trivial. ANOVA is just going to use those 2 methods of looking at the standard deviation of means. So we can imagine doing a direct calculation. We get a sample, we have a sample mean. We get another sample under identical conditions, and we get another estimate of the sample mean, and so on. And we can just calculate the standard deviation of those sample means. Okay, so we take the sum of the squares of them and divide by the degrees of freedom associated with them. We're just calculating a standard deviation of the sample means, and we can call it the standard error of those means. We can also do it using a single sample method. This is the one where in first and second year, when you're calculating standard errors of the mean, is the one that you use. In the background notes, for those who know a little bit of maths, it's quite easy to prove that it will indeed be your sample estimate divided by the square root of n. Okay, and that's an indirect single sample method of calculating the same number, or what should be the same number. Okay, so we're now coming back. So the t-values are always estimating the distance between a sample mean or 2 sample means, the difference of the mean of the difference of observations. We calculate the standard error using the single sample method. So we just take the standard deviation divided by the square root of n. And we're going to lose a degree of freedom because to calculate that standard deviation, we still have to calculate the mean. Okay. That's it. We've now got the critical bits. We can measure that distance, the top bit, how far 2 means are apart, how far a mean is from a hypothesized mean, how far the mean difference is from 0. We can calculate the standard error of that metric, convert it into a t-score, which is like a z-score, but it's just as a distribution of that number. It's slightly broader, and ask for the probability. Okay, so are 2 means the same? So we have 2 samples, nominally under condition 1 and condition 2, and we can ask, are they the same? If you remember, what we're doing here is assuming a normal distribution. We're assuming this cascade-like thing of processes that's going on. So if we make that assumption, and it's perfectly reasonable, we don't just have one neuron at the front of the head and one neuron at the back and it does everything. There's a whole lot of processes go on in between. What we're really asking when we're doing an experimental manipulation is, have we managed to change one or more of those processes? Have we managed to bias the dependent variable, our output measure, either down a little bit or up a bit by the change that we have done externally, the change that we've manipulated experimentally? So we're targeting a process, set of processes, and if we can make one outcome more likely than the other, depending on the condition, then what will happen is that the dependent variable will shift. Critically, with a large number of processes, it's just a shift. It will still have exactly the same shape, the same spread, but it will just be shifted. Okay? And this is where the assumption of the homogeneity of variances comes from. For a t-test to work, the spreads need to be the same. The only change is a shift in the spread of those distributions. Okay, so now we collect samples, and we assume that we're collecting the one from the red line and one from the blue line, if you like, from two samples, two distributions, and we want to ask if those distributions are the same. What we're expecting to see would be something where perhaps there's a shift in the distributions, and it could be quite small, that shift. We're just trying to detect if there's a shift. Now, because we're assuming those distributions are identically shaped, the only parameter that can change is the mean. Of course, that's what we've done by targeting that process. We've just changed the means, kept everything else the same. So we can sensibly ask, are the distributions the same, by asking, are the means the same? So we're going to do exactly the same as we always do. How many standard deviations are the two data points apart? And what we want to know is the standard deviation of the difference between the means, rather than when we're testing against a hypothesized case where we just need to know the standard deviation of our variable. Here we have to answer, what's the standard deviation of the difference between the means? The best method, when we say best, we mean the most powerful one, the one that maximizes the chance of detecting a difference, if there is one, is with this assumption that those spreads of the two distributions are the same. Okay, so it makes an IID, independent and identically distributed distributions. What we do to check if that is the case is look at Levene's test. I know that Kira went over this, showed you how to do this in the second year. Okay, so if they are not the same, then there's really two options. One is called Welch's version, and the other is to correct using Satterthwaite's correction. It's the standard way. Welch's version calculates the variance, standard deviation of the difference between the means, in a slightly more conservative way. It makes the number bigger. So it ends up being less powerful. There's a fewer number of standard deviations if you calculate the standard deviation using Welch's method. Here is an important message to take home. When we're running an experiment, what we really want to ask is, are the two distributions we get the same? If you find that the variances are different, you should not go, oh no, I've got to use Satterthwaite's correction to find out if the means are different. You've actually already answered the question that you set out to. Yes, the distributions are different. They differ in their variances. So when we're running tests, we want to be finding and answering the question as we've posed it, and we can use Levene's test to answer the question, are the distributions the same? It might not be what we're expecting, but at least it's something where it says that there's a difference that's systematic between these two conditions. So the answer is, if Levene's test is significant, it doesn't actually matter what Satterthwaite's correction then says when you use it. We've got a difference in between our conditions, just not the one that we're expecting. So use Levene's test. If P is less than 0.05, use the Satterthwaite's correction. SPSS churns that out as a default in its output. And then you can certainly say, if Levene's test is significant, that the variances differ. And perhaps in addition to the variances differing, there might be a difference in the means. If Levene's test is non-significant, P greater than 0.05, then you just have to use the uncorrected version, which is using this most powerful method, a pooled. You often see people talking about pooled estimate. So it assumes and adds all of the data together and treats them in one go. Because there's now a much larger sample size, it gives you a better, more powerful, better estimate of standard deviation, which means it'll be more powerful in detecting differences. The final one, as I said at the beginning, is really just another test against a hypothesized mean, the paired or within subjects t-test. It's the one where you take a difference, so you get different scores, and then you test those against 0. Okay, so it's really doing against taking the differences. Now you've got a single sample of differences which you're testing against 0, against a hypothesized mean that there is no systematic difference between them. Note that what this difference score is doing is comparing these two scores. So it's taking out any effect of the participant. If we were looking at, say, reaction time, if participant 1 was much faster than participant 2, you've got variability here due to differences in participants. What we're asking is there a systematic difference score? Which means now that each participant starts off with a hypothesized difference of 0. So it doesn't matter what the differences are between participants, we've removed that effect. I'll be coming back to that in next week's lecture. Okay, so again, we just have to calculate, we know the average difference, and we just have to calculate the standard deviation of those differences. And so it's very simply back to what is the standard deviation of the different scores. Express that like a z-score, but remember it's a t-distribution, and then get the computer to tell us the probability of getting that t-score or more extreme. So we've got 3 variants of t-tests. All that varies between them really is the number that you put into them. But we're always expressing the distances between 2 points. One might be hypothesized mean, typically of 0 or not. But the distance between two things is the number of standard deviations of that distribution. We should report it using t, then give the degrees of freedom equals t-value. Don't go mad with decimal places. 2 is more than enough. And if your t-value is 173, don't bother with 173.12. So think of it as 3 significant digits when you're reporting on t-values, f-values. P-values, never go more than 3 or 4 decimal places. And again, if the p-value is quite big, so p is 0.21, you don't have to report the next sets of decimal places, because what we're looking for is that magic p less than 0.05. I can't resist smashing up sticks, can I? Okay, remember that a t-score, a t-test, is really doing a z-score. It's an approximation to a z-score. So we're expressing these distances as the number of standard deviations, the standard errors of those differences. T-tests assume there's normal distributions. Okay, so if the sample distributions aren't normal, then determining the p-values becomes a little bit mute. All bets are really off unless you know that underlying distribution. But the t-test is comparing means, and there's this wonderful beast called the central limit theorem. And the central limit theorem simply states that if you're looking at means, the distribution of those means is always going to be normally distributed. It doesn't matter about the underlying distributions. It doesn't matter about their shape that's there. And that gives us some comfort. The problem is that it's a matter of at what sample size that happens. And the only case that we know to be true is in the limit, so with an infinite sample size. For most practical purposes, the sample size doesn't have to be that big, it seems. But there is no simple way of knowing about it. So it's always worth just looking at the shapes of the distributions, and most times you'll find that it looks vaguely normal, and you're fine. Every now and again you'll get distributions which are so clearly not normal that you should be concerned. You still run the tests, but now you just phrase the interpretation in a different way. Show the reader that the distributions are clearly not normal, and then you just say there is a suggestion of significance if the p-value is less than 0.05. And equally, there is a suggestion that the effect was non-significant if there's non-significance, if the p-value becomes greater than 0.05. It works both ways, we just don't know. Okay. But it is the case that the central limit theorem means that a t-test is dealing with differences of means, and so the normality assumption is not as important as you would have thought. That's a sort of technical mathematical one. The real problem with t-tests is that there's two means. There's two samples that you're dealing with. And this is what Fisher solved. He worked at Rothamsted. They have a huge picture of him in Rothamsted Experimental Station. Years ago at York I did a master's in computational biology, as it happens, but we went to Rothamsted Station. I found out from Akira's talk, he's one, there's Richard Feynman, if any of you heard of him, who can think, genuinely think in multiple dimensions, so more than 3. Fisher was evidently another one. They're very, very rare people. And he just dreamt up ANOVA, sort of sitting there thinking about the problems because he could think in multiple dimensions, could see distributions not just as a curve or as a sort of blob, but going off into weird dimensions. And he's come up with ANOVA, which is really the grandfather, it's the big one of the idea of a t-test. Okay, when we're dealing with ANOVA, it's much easier if we change the terminology, and then hopefully you can see, it'll help you see why a t-test is just an ANOVA. So rather than having groups or conditions, we're going to have levels of a factor. Okay, so that this will allow us to have 2 factors, which is a 2-way ANOVA and so on. It allows us to expand the number of dimensions in which we're thinking. And so we want to call the levels within it, the different conditions within it, we'll call them levels of the factor. Okay. The first thing that I'll take you through is that if we just square t, we'll end up with an F ratio. We'll end up with the ANOVA version of it. And I'll take you through some of the model, the underlying idea behind the one-way ANOVA. So now we're doing another experiment, but this time rather than just having 2 levels, we're going to try and influence sets of processes in multiple ways. Maybe one we think will lead to a decrease in our dependent variable, another an increase. And we have one that's in the middle, the neutral condition. Okay, so that's the only change conceptually that we're doing, is we're adding in another condition. And it's going to influence process or set of processes in more than one way. So now we'll end up, instead of having two identically distributed distributions with different means, different positions along the dependent variable, we have 3 or 4 or 5, however many it is. So we've just got more than 2. In a t-test, we're calculating with 2 means, so we'll start with ANOVA with just 2 distributions. Okay. Now we're going to use, instead of the distance between the means, we're going to use the variance between the means. Okay. And we can calculate that variance of the means by the direct method. We've got 2 of the values, we can take their difference and square it. Okay, that's just the distance between the means squared on the top part of our little equation that we're going to come up with. Okay, so any observed value that we have, so something that we get, we can think of as being in a model, a theoretical model of what's going on. We can now calculate all of the sums of squares. So if you remember, the ANOVA's using the sums of squares of the means, so how the means differ from the grand mean, summed together and squared and so on. And we can have our between levels, so SS between, is an indicator of the variability between the levels of the means. It's our direct method. We have the sums of squares for the error term, pooled estimate, so taking each datum from the mean of its condition, taking that distance and squaring it, and adding them all together for every data point. And we've got the sums of squares in total, so the distance of each data point from the grand mean, and those all add up. This is what Fisher, I think, probably just saw, was that all of these sums of squares will always keep adding. Now, what we do now is when we calculate our F ratio is that we do the divisions by variances. We calculate the variances. There used to be a statistic called an A statistic, which was you ignore, you don't create everything into variance, because variance is just the sums of squares divided by the degrees of freedom, the average square distance. And you don't need to do that, but that was in the days when everything was done by hand. And any step that you did that you didn't have to do by a calculator, but could look it up on a table, you did. Nowadays, we convert these sums of squares into their variance measures and get the ratios. What this means, so what I'm showing here is in the Venn diagram, the circle, is the notion of all the variability of the data. Okay? And we're saying that we can attribute that variability to 2 things. One, the sums of squares between, is the variability that's due to the being in one condition or another. If you've got 3 conditions in being condition 1 or condition 2 or condition 3. So that's our sums of squares between, our direct method. Okay, so we've got these 2 sources of variability. And we're just asking with an F ratio how big that red area is compared to the error term. So you'll often come across the F ratio as the variance of the error plus the variance due to the level, the variance of the effect, divided by the variance of the error. Okay, so that's actually what it's always measuring, and if this bit gets big, then the F ratio is bigger than 1. So if there's variation due to the level, due to the differences in the means, compared to the error term, variance of the expected error of those means, then we can say that there is an effect, that the level effect is big compared to the error term. The output from an ANOVA table varies, of course, depending on whether you're a psychologist, a biologist, a physicist, a chemist. They all use different terms. There is the between levels effect, the sums of squares being SS between. We have degrees of freedom, and they can give you the sums of squares divided by the degrees of freedom for the mean square between. The next row down will be due to the error term, sums of squares, degrees of freedom, mean square error. The F ratio is this number divided by this, and the p-value is the probability that that F ratio equals 1. Okay. We are only interested when the F ratio gets to be bigger than 1. There is a value for very, very small F ratios, which is when the variance between the means is much smaller than we would expect. It is a very weird construct, and everyone quite sensibly ignores it. It means that your conditions are somehow non-independent. Okay, and if you've done a sensible design, you know that is just by chance. So we ignore that condition where you've somehow made the variance that you observe smaller, significantly smaller than you would expect. The most annoying thing is that labels in ANOVA tables vary. I'm not quite sure what SPSS is calling all of these things these days. Between levels is often given just as the factor names, was what SPSS used to do. You will sometimes see people call the error term the within subjects error. It's the most confusing term ever. And when you're using SPSS, do not be tempted to use the option of compare means one-way ANOVAs. Always go to the general linear model route and run them. And if you remember, a t-test is just an ANOVA with 2 levels. You take the square roots of everything. So you never need to use that compare means option in there. There's things on the web pages of how you can run this, run it using the general linear models. The reason for doing it is that once you get into the habit of always going down there, you can always do the analysis in that way. Next semester you'll find another way of always going down and doing it as a regression. If you remember when I talked about the bivariate, you can think of ANOVAs as a regression method. Let us stop for 10 minutes and then get back to it. And I'll talk about effect size. Okay, so as always, p-values just tell us whether we would expect to see the value by chance or not. And the problem is that p depends critically not only on the effect size, but also on the degrees of freedom, on the sample size. So we should always give something where we're trying to describe the size of an effect, hence it's called the effect size, as well as the p-value. And what we want to do, as always, is standardize or normalize effect sizes so that we can compare them from one study to another, in the same way that we standardize all normal distributions with a z-score and so on. We want to standardize effect sizes, and what we can do is use the R-squared value. Remember, this comes from the regression-like properties of ANOVA. And what we want to know is the proportion of the variability in our dependent variable that we can explain, that we can know about, that we can model, however you want to phrase it, of knowing our independent variable. In regression, that independent variable is the predictor variable, and it's a continuous one. With ANOVA, it's discrete, so it's the levels of, so knowing the level of. And what we can explain, well, we know what we can't explain, and that's always the error term. We can't explain the variability of data around that condition's mean. So that's the bit that we can never explain. And so the total variability that we can explain is always 1 minus the sums of squares of the error term divided by the sums of squares, total sums of squares. That's the bit that's left over. It happens that in a one-way ANOVA, that's the sums of squares between divided by the sums of squares of total. But we should think of the R squared as just being the bit of the variability, or 1 minus the bit of the variability that we can't explain. The error term, the residuals, the distances from the line in regression to the data points. That's the bit we can't explain. Again, while it's often given like this, sums of squares between divided by sums of squares of total, it doesn't help when you start thinking of slightly more complex ANOVA designs, more complex regressions. Put in 2 predictors, and that idea no longer holds. What we're interested in is what the error term is, and then anything other than the error term we can explain. So our R squared is 1 minus the error term divided by the total sums of squares. Remember, you don't have to know these things. This is just for me to explain it to you. The text is the important part of it. We're going to use a normalized value, so it's going to go from 0 to 1. It's the proportion of the total variability that is explained by knowing which level the data belongs to. So what level, what value of the predictor the data belongs to. And we can calculate it by using the variability that we haven't explained, the variability of the data points around their condition means, and that's the error term. Okay. Fisher, the guy who did the ANOVA, came up with the idea, was interested in the experiment, the study that you have run. Okay, and that's what that R squared value is. It's the thing that in your study that you have run. However, if you remember that the F ratio and so on, what you've got on the top line is the error term plus the effect of the levels divided by the variance of the error term. You've actually got a confound in there. And we use the term adjusted R squared to say, well, hang on, we could estimate that the error term correctly. We could estimate the error term by itself in isolation. And to do that, you take that mean square error, the expected error term, and you subtract out the degrees of freedom of the between condition, so the n minus 1 of your levels. That gives you an estimate, an adjusted R squared, of the proportion of the variance in the population that you would expect to be able to explain. Okay, so not just in your study, but what about in the population at large? What you've got in that estimate from your study includes the erroneous amount. Okay, so you shrink the error term because some of what you've got in the population you think that you could explain otherwise. The danger of this is it is an estimate. The adjusted R squared can result in a negative value. Okay, it looks as though you would explain less than 0, which is not possible with variance. It's squared. It is just an estimate. And in general, when we are doing studies, we as a discipline are not interested in the adjusted R squared. We're talking about the study that we have done. We're describing what we have done. Other areas, particularly those that deal with very large data sets and are trying to make genuine estimates, so more in the social sciences, not social psychology, but social sciences, make use of the adjusted R squared. Depending on the discipline that you are working in, you will either report one or the other. we should always report the effect size as the R squared value. Having said that, we'll now start talking about eta squared. Again, this is looking ahead to when the ANOVAs get more complicated. So eta squared and R squared are the same thing in a one-way ANOVA because there's one effect. There's eta squared generally refers to the proportion of the total variability that your effect explains. So it's the sums of squares of the effect divided by the total sums of squares. And with one-way ANOVA, there is only one sums of squares of an effect. There's only one factor that you're looking at. But we use eta squared to refer to the proportion of variance in the data explained by a single factor or an interaction term, so one component. And we use R squared to refer to the total model, the total ideas that we've put in there. How much can we explain of the total variability, regardless of where it is our R squared measure. We then use a change of nomenclature to talk about eta squared, and R squared is the sum of all of your eta squares. And we'll come back to effect size and talk about the thing that SPSS puts out, which is the partial eta squared. And for one-way ANOVA, partial eta squared is eta squared, which is R squared. So it's a unique case. Partial eta squared is a slightly different conceptualization. One-way ANOVAs, they're an extension to a t-test that allow for two or more levels to be looked at. Indeed, a t-test is a sort of ANOVA. Call it a different thing, it was invented by somebody, it's different, but it's subsumed by ANOVA, and I really would recommend always running these comparisons of means rather than compare means in SPSS. Go to the general linear model route. You get into the habit of doing it through that way, and you get very familiar with how to put the values in, rather than having to go, oh, I'm going to do a t-test, which t-test? They look different to each other, and then I'm going to do an ANOVA. One-way ANOVA is in that compare means group, but then two ways you have to learn something new. So rather than learning 4 or 5 different menu systems, all of which are doing the same thing, use the ANOVA general linear model ones. For ANOVA to work, for the p-value to be meaningful, we have to assume that the scores are normally distributed with equal variances and independent. So IID, independent and identically distributed. What it's doing is partitioning the variability into its component parts. It's saying that there's a total variability, and this is made up of 2 things in there. It's made up of the error variability and the variability between the means. That's the intrinsic noise variability. The F ratio says, well, if there is no difference between the means, then we should get 2 estimates of the same thing, the error variability. But instead of taking the error variability, we'll take that error variability divided by the square root of n to get the variability of the means and take those ratios. So we'll have 2 standard error of the mean estimates. And under the assumption that there are no differences between the population means, so any difference is just due to my sampling, the ratio should be 1. Can of course reverse, if you like to think of that logic, if it helps you in another way, by saying that the variance that you see between the means, you could multiply by the square root of n and end up with an estimate of the error noise, the error variability, and take the ratio of those 2. They're the same things, there's just a root n factor in between them. Okay, so we're going to use that idea of separating out variability In the next lecture, I'll be talking a lot more about using those Venn diagrams. So start to try and think about variability as just being variability, just a lump. Okay, there's a whole lots of sums of squares in it, and some of those squares, some of those distances squared, we can attribute to some things, and other bits we can't. So we can partition out variability. As always, degrees of freedom, you just lose one for every mean that you have to calculate. We're going to take two estimates of the standard error of the mean, the direct and indirect calculations, and ask us if their ratio is 1. I assume F ratio because of Fisher's. I assume it's called Fisher's ratio. Everyone refers to it as the F ratio. F1 will approach 1 if the level means are equal. That is, if the population means are equal. That value will get closer and closer to 1. And if they're not, it'll get further and further apart. Okay, so what we are checking is whether the F value, we're asking the probability of getting any F value greater than the observed value, so our statistic, given that the variance in the levels is 0. So that's the formal thing that an F ratio is testing. The variance of the levels are only 0 when all of them are the same. We're actually looking at the variance of the different levels of our factor. If you've run a test and you've got an F ratio and then you run it with a greater sample size, you actually can use that F ratio as a secondary test. If your sample size F ratio increases compared to your first one, you probably have an effect. And if the sample ratio decreases, you probably don't, regardless of the p-values. Okay, so that this F approaches 1 if the means are equal. So the bigger and bigger your sample size, the closer and closer to 1 that it gets. The null hypothesis is true, and this is your null hypothesis. The variance of the levels equals 0. Okay, so we're just looking at is the variance of the level means 0? Are all the means the same? We're going to do it via variance. How do you report an F ratio? Well, there's an F, then you need to give the degrees of freedom, and there are 2 degrees of freedom. One is the degrees of freedom between the level means, the degrees of freedom used to calculate the direct estimate of the standard error of the mean squared. The other one is the degrees of freedom in calculating the error term, the variability about the level means. Okay, so you get F, degrees of freedom between, comma, degrees of freedom of error. If that comes out as being F, 1, comma, and then another number, you're actually doing a t-test. Okay, so that indicates to the reader it's essentially a t-test. How big is the difference? There'll be an associated p-value with that, of course. How big is the difference between the means? This is the effect size. This is the thing that sort of matters. Use eta squared or r squared to describe the effect size. There's another one in there of omega squared, which is another form of correction that can be used. Stick with, or the adjusted r squared to the effect size in the population. We rarely are interested in that. We're rarely interested as psychologists in how much of the variability in the population might we explain if we went out to the entire population. We're interested in what happened in our study. When we've done it, what happened and how does that compare? Finished nicely, even earlier than I was expecting to. Okay, so I will see some of you this afternoon. Remember, the quiz will come on at 5 o'clock this afternoon, stroke this evening. It lasts until Sunday at midnight. So I think it's actually 5 minutes past, so 5 minutes into next Monday. You've got the week to do it. As far as I know, you can indeed log off and log back in. Several people are nodding, you've checked it. I've asked people and they've all said that they can. There is always the chance that something weird will happen. So I know that one person, when they downloaded a data set, it didn't look like just a set of numbers. And for some reason completely unknown to me, it was downloading a web page. Don't ask me why. They logged out and logged back in, and it didn't work. When they closed their browser down, it then allowed them to get hold of the data file. If you're getting trouble, so if you're trying to download a data set and it's just looking weird, let me know, and I can reset where you are. It will mean you'll have to do the content-based, the conceptual-based MCQ set again, because it's just a random sample that comes out each time you run the test. It should all work. Okay, you should be able to come in and out as you want.
How many questions are there?
There's 10 and then 3 data sets, and the questions include today's lecture. But you've got, there's lots of time available because you can go in and out of it. It saves answers when you go click to next page. Yeah, so they will come up in blocks of 5, I think I've set it out. So you have to do 5, and then when you go next, those sets of responses are saved. If you haven't finished a page worth, when you come back in, you'll have to start again. It'll be the same questions though.
After this save them, we can always come back and change the...
Yes, you can, yeah, it's not... the only time it finishes is when you click submit. That's the point where you won't be allowed back in to redo it. It should give you your score out of 20. It has got negative marking. It's exactly the same as the practice ones. You could, if you're feeling completely mad, do the practice ones, I don't know, 50, 100 times, and you will see pretty much every question that's going to be there. So it's the same set of questions, so the practice ones really are practice on the questions you might get in the test. I really don't recommend it. There's several hundred questions, several hundred. Yeah, you'd have to do it an awful lot of times on the practice ones to make sure you've seen each one.
So when you say it saves when you come out of it, do you just like cross off your browser, or like is there some way, like how does it save?
Once you click the next, it stores where you are internally.
So then if you wanted to stop, then you just like cross off your...
You just close down the browser, and then if you come back to it, it'll put you back in with where you've got to filled in. Make use of each other, make use of the web. So part of these things is for you to practice finding out answers to things which aren't readily available. So use Andy Field's textbook. There's nothing I'm covering that isn't in his textbook. There are a few questions which aren't covered in my slides, which are in either the first year notes, the second year notes, and the textbook. I always find looking through textbooks, it sits on my office, it looks as though it's being used because it's sort of flopping over a bit. I find that using the internet is much quicker. Do not take the single answer that you first see. Check somewhere on another site, but that's often quicker than using textbooks for the things. So I really don't mind how you answer the questions. It's just for you to get used to answering the questions, and so you also have the practice ones, and to get familiar with running the analyses. By the end of this module, the idea is that when it comes to SPSS, you go, yes, I can use it. And so the next module, when Ken says, can you use SPSS? It's like, yes, you know that general linear model route and how you use what's in there. Then Ken will take you down the correlation and regression one and the factor analysis one. Okay, so it's just to make it, for you to show competency at running tests and finding information. So I'm hoping that you will all do well. It's not going to be the end of the world if you don't, all you have to do is pass the continuous assessment component in total, and this is only some 20%, I think, of the continuous assessment. The majority of the mark will be on your individual write-up of the project. Is that all clear as mud?